Okay, everybody, we are back and we got so much for you today. We got the 2 sample tests coming up for mean and proportion, and then we are also going to wrap up just the 1 sample test for proportion as well. So let's get to it here. So first thing we're going to do is the 1 sample test for proportion. It's kind of wrapping up from last time. So it's identical to a Z-test for means, which we've done lots of so far, except in this case, we're testing for a proportion or percentage. So I spelt it wrong. Proportion or percentage. So yes, indeed, we have a new formula. It's this one here. This is p hat minus PO, and it's all divided by the square root of PO times 1 minus PO divided by N. Oh, there you have it. Now, p hat is calculated as x divided by n, so you'll be watching out in the question for some sort of, percentage, like 23 out of 50 people surveyed, whatever, something like that. Everything else is going to be the same as far as right, left, and two-tailed rejection regions, so, they remain the same. And this test is used in the case of a binomial hypothesis testing. So watch out for questions that have dichotomies, okay? So, people voted yes or no, or people preferred, product A over product B, and so you'll have sort of a binomial situation, but it'll be a hypothesis test. On to the next slide. So here is an example that we can do right off the hop. It's an iSurgeon one, so I'll give you a moment to pause. You can read through here. I'm just going to highlight, I recommend you read it, and now I'm going to just highlight the important things. So we've got these iSurgeons, and we have a risky operation that restores sight. Okay, so they hope to monetize their method by showing it's better than the old method. Okay, so under the old method, 30% of patients who undergo it will recover their eyesight. And so here comes the experiment. So surgeons have performed this their surgery 225 times using the new method, and 88 have been successful. Can we justify the claim that the new method is better than the old one at the 1% level? Okay, so right here, you got your p hat, right? 88 divided by 225, and it's binomial because either the surgery works or it doesn't, right? It restores the eyesight or it does not. So here we go. First things first, figure out your HO and your HA. HA is easier to figure out. Now, you actually need to go and figure out what that p hat is. Okay, so just over here off to the side, I'm just going to go say, well, p hat is, there was 88 over 225. Okay, and p hat, if you go calculate that out on your calculator, go ahead, you get 0.39. Okay, now that's what they found in the experiment. If you go back and look in the question, they are wondering if the proportion is greater than 0.3. That's the old method. Okay, and that is right here in the question, only 30% recover. Okay, so we're trying to show that the proportion for the new test is greater than that, and then the HA is just going to be, well, the proportion is equal to 0.3. All these things are on the formula sheet. Now, as far as the rejection region, well, it's pointing in that direction. So this is a right tail test, right? So right tail. And it is at the 1% level. So we're going to be looking for Z alpha of 0.01. And then we can go ahead and figure that out. I recommend using the t-table. Here it is. So Z table. T-table, right? Go down all the way to degrees of freedom infinity. Find 0.01, 2.326. Wunderbar. So 2.326. And, if I was to draw a nice little, normal distribution, just very briefly, right tail test. This is the rejection region at Z equal 2.326. And over here we reject H. Oh, perfect. over here we accept HO. Now I've gone ahead and written down the formula for you from the formula sheet, so it's all there. We already calculated p hat over here. You'll notice the formula needs 1 minus PO. And remember, PO is what's given in the question here, so we can go 1 minus PO, and that's going to be 1 minus 0.3, so this is going to be 0.7. So that's the number we'll use in the formula. We have p hat already, we have PO, we got everything we need. So p hat was 0.39, PO was 0.3, divided by big square root sign. And so PO was 0.3. In the brackets, we got 0.7 divided by the n. Now, n was 225 from the question. Okay, pop that in your calculator and give you a moment here, but you could pause. So you get 2.95. And that's great. And that's great. We're doing great. This is perfect. So since z is equal to 2.95 and z alpha was 2.326, and 2.95 is what? Is it greater than this or less than? Well, it's greater than 2.326. So we'll be landing in our rejection region. So we are going to reject HO. So reject HO and accept HA. Don't forget your concluding statement. So at the 1% level of significance, the sample evidence, ooh, am I really going to type this out? I'm going to try. So it shows that the proportion of eye surgeries, I suppose, using the new method. So using the new method has a success rate greater than the old surgery. I'm going to say the old surgery method, whatever. So there you have it. Be very careful how you phrase this, right? So we can't actually say, as usual, that it is 0.39. All we can say is that at the 1% level of significance, the new surgery does indeed have a higher success rate than the old surgery. So very subtle, but important. We're ready on slide 6. This is great. So now we're into sort of, I guess, brand new material, so to speak. It's still hypothesis testing. We're going to be testing the difference between two means, independent samples. So obviously, the samples must be independent is already one thing we know about this. So if you ever need to compare two populations, like maybe, remember, population doesn't mean people necessarily, but it could be, you know, comparing the mean gas mileage for two different cars, or maybe crime rates for two different cities. We're going to consider the sampling distribution of the first population minus the second population mean. And thanks to the central limit theorem, when sample sizes are large, the sampling distribution of these two means being subtracted is approximately normal. So that the mean mu is going to be approximately equal. What this is basically saying is that when the population sizes are big enough, even if we have a sample, that those samples will be approximately pretty dang close to the actual population means. And this is the standard deviation. Remember, standard deviation is always a bit tricky. Standard error, right? So standard deviation is a bit more complicated. We have to average those out as well and do the square root. So, I mean, it's kind of like, all right, that's great. What's the formula? So, a little bit more, though, before we get there. So, populations have to be independent. This is super important. So, independent means there's nothing that links them together. Like, you know, one variable goes up in one and it affects something in the other population. So, no relationship between subjects in each sample. So, the populations must be normally distributed. Yeah! We love the normal distribution. Normally distributed, and the population standard deviations must be known. So we do need to know those. as long as both samples are large. If these are not known, so if you don't know the sample standard deviations, they can be substituted with the sample standard deviations. Okay? So that's good news. That's good news. All right. So how do we write the hypothesis for this? Because it's going to be a little bit different. So for the null hypothesis, we actually assume there is no difference between the populations. Right, so the status quo would be, you know, you got these two cars that are in the same class. They're both SUVs with V6 engines. Now, there's really no huge difference between their gas mileage. Okay, so that would be the status quo. So this is HO. And we're trying to prove otherwise. The choice of populations is arbitrary. So what I mean is, you got two populations. You're going to have to call one of them mu1 and the other one mu2. Doesn't matter which one is which, but keep in mind that, say if you're comparing notes with someone else and they named the populations the other way, it is going to change their work a little bit, okay? It's going to affect whether you're doing a right tail or a left tail test, and it's going to change some of the signs on your numbers, okay? So keep in mind that you consistently label everything consistently between the two populations. What else? The last point. Yeah, the null hypothesis will always contain symbols and no numbers, since we will not know what the hypothesized mean is for the two populations. So seeing is believing. So let's see. What's the formula? So here's the formula if you're comparing two samples. So Z equals, now we're going to go X bar 1 minus X bar 2. Subtract DO divided by, woo. This is basically the averaged standard deviations, right? So we've seen that before. Now DO is mu1 minus mu2. Now this is a correction factor. It's in the book, so I wanted to mention it. Now the good news is we don't really do this very much. I just wanted you to be aware of it because it is in some formulas and other textbooks. It's a correction factor. We don't use it. It's going to be 0 in the questions we do. So since the difference between the population means is 0 by the null hypothesis, right? This doesn't really appear in the formula. So DO is 0 if it's not mentioned in the question, and I don't really give questions that involve it. So all the other steps are the same as before. I think there might be like one question in the homework where I gave one just so you guys could see one, okay, but not something that will necessarily show up on a test. So here's a two-sample mean example. So give you a moment, pause the video, read it out. So yeah, we got a bank that has a current system that yields a customer wait time of this many minutes. So taken from a random sample of 100 customers. Then they have a new system that's sampled 100 times, and it seems that the new wait time is about 5 minutes. So assume a population variance. Be careful, it's not standard deviation. They gave us the variance of 4.7 minutes for the current system and 1.9 minutes for the new system. So when I say you got to keep your numbers straight, you got to really keep your numbers straight. So write yourself a nice list, okay? Test the hypothesis that the new system is faster than the current system at the 1% level. Oh, yeah, we can do that. We love to do that. So, what is HO? In the two sample mean hypothesis testing questions, HO is always going to be one of two things. There's two ways to write it. You can write mu1 minus mu2 equals 0, right? Remember, the status quo is that the difference between the means is 0. That's one way of writing it. You could write it as mu1 equal mu2. Now, let me go check my formula sheet here. So here's the one for proportion that we did previous, and here we are. Two sample tests for mean, and yeah, in my formula sheet, I wrote it like this. So mu1 equal mu2. It's fine if you write it like this, or if you write it the other way. Okay. Now, if you look at your options for the other one, again, there's two ways to write it, but I prefer this method, where you're saying, well, one population is greater than the other, one population is less than the other, or they're not equal. Okay. Yeah. Good. What we got here? So what is our HA in this case? Well, if you go back, it says, well, and again, it depends which one's going to be mu1. Okay, so it really matters. Which population are you calling mu1? So if we just go in the order of the question and just kind of say, okay, well, mu1 is going to be this one. It's going to be the system that has that waiting time, a sample size of 100, and be careful because they gave us variance, so that's standard deviation squared. Assume the population variance is 4.7 minutes for the current system. Okay, so that would be the old one. Okay, so if we call that one mu1, and then this one down here mu2, so if mu2 is the one that's 5.14, again, also sampled 100 people, and they gave us the variance as 1.9, so standard deviation squared. Okay, so if that's the case, we're testing to see if the new system is faster than the old system. So if the new system's faster, that means that mu1 would be greater than mu2, right? Because if this is slower, mu1's slower, so the time here will be greater than the time for mu2. That's tricky. It's pretty easy to mess that up and get that backwards. Okay, so there it is. So if we're doing it this way, then it's going to be a left tail test because it's pointing to the left. Okay, now on this picture, I wanted a 1% level of significance, and so this is wrong because this is a 5%. Okay, so alpha is actually 0.01. I just kind of threw this in from just anywhere in the book, so I just, so this is 0.99%. Yeah, so level, 1% level, go look up Z at 0.01. Go use your t-table, right? We just did this for the last question. It's the same. So 0.01. Degrees of freedom infinity, 2.326. So 2.326. All right. You can write your little rejection statement. So, if Z is greater than 2.326, reject HO. I suggest you actually don't do it shorthand. I kind of did it with just shorthand, but there it is. Now, we have everything we need, more or less. All right, assuming that, well, this is mu1 squared. Oh, sorry, I said mu, but I meant standard deviation. So standard deviation of the first population, and these are not standard deviations, these are the variance. Now, you'll actually notice that in the formula, we're taking the standard deviation and squaring it. So they are giving that to us already, so we don't need to change these numbers. Be very careful because there's so many ways that it can be given. You have to be very careful. The DO factor is 0, right? So that's gone. And now we can go ahead and basically plug in our numbers. So remember, x bar 1 or mu1 was 8.79. Subtract x bar 2 or mu2, which was 5.14. DO is 0, so we'll just not write it. And then we got the square root of all this stuff. Now, the variance of the first population is 4.7. The n value was 100 plus 1, was it 1.7 or 1.9? I got 1.7, but I think I might have made a mistake. Yeah, it's 1.9. So it's 1.9. I probably could have kept that. I could have changed it to a 9. Nobody would have noticed. There, yeah, 1.9. My bad. There, so you have it. I suggest you pause the video, plug it in on your calculator. This is enough work. However, if you want an intermediate step, you get 3.65 in the top and 0.2569 in the bottom for a grand total of wowzers 14.21. What does this mean for us? Now, when you get such a big number, I try not to give you wacky numbers. Sometimes it happens. So I believe I made this question up, so the numbers were a little wacky. It happens though in real life. It does. I've seen it. Yeah, we have really big Z score. So what does it mean? Well, is 14.21 greater than 2.326? Yeah, it is. So since Z is 14.21, and that's greater than Z alpha equal 2.326, what do? We reject HO. And accept HA. Okay, so what can we conclude? So we say, hey, at the 1% level, the new system, let's throw in an extra word, the new wait time system is what? Well, we can't make any claims as the actual numbers, but we can say the new wait time system is faster. Faster than the old one. Get out of here, old system. You were no good. There we go. So, that's all you can say. And we are about halfway through. This is great. Yes, I kind of said what if DO is not 0. Well, I suppose I'll throw this in, but again, I just want to stress that, basically, yeah, no, we can actually safely skip all this. That's good news. One of the small changes I've made for, our COVID world is we don't need to worry about this. So I'm going to skip this, which means that we skip the next example. So yeah, we can skip it. You can certainly go check out the notes. I do have these notes online. I just won't do it for the video, so we're going to skip this slide. And what do we got here? Yeah. Yes, well, now we're going to do proportions. So, quick step back here, just to make sure we're all good. So what we have done, is we looked at 2 sample tests for mean, and you'll notice that there is a t-test version of it, which is a bit more involved, which I believe comes up next time or something like that. Or just watch me be wrong. It'll be in this lesson. It might be. Let me look ahead. I don't think so. I feel like usually... no, I'm a liar. No, we totally... Do we? No, we don't. Looking ahead. No, I'm a liar. We do it today. Okay, good. So we will do the t-test today. Yes, we will do this one as well. Basically, it's just more calculations. So if sigma's unknown and our populations are small, then we turn to the t-tables, and the formula looks a bit different. So we'll get there when we get there. But right now we're gonna look at sample, 2 sample for proportion. Okay, what's the difference? Well, not a lot. Symbols are different. We use p for proportion. I'll use p hat 1 and p hat 2, which is the actual fractions. And then we have this p hat down here that doesn't have a number, which is basically the average of the favorable outcome, basically. So x1 plus x2 divided by the total sample size between the 2 populations. So yeah, a little bit more work. Well, that's okay. We love work. So let's take a look. What do we got? Yes, sometimes we need to compare 2 probabilities of success. Yes. Therefore, we need to consider the sampling distribution of p hat 1 minus p hat 2 as a point estimate for the actual population ones. That's what that means. The central limit theorem still applies, so the sampling distribution is basically approximately normal, with our sample means being equal to our population proportions, with this being our standard deviation. Yowza! Ugh, that's ugly. But there you have it. Alright. So what is the standard error of the differences for sample proportions? So since the 2 population proportions are unknown, we need to estimate them. The best estimate for p is obtained by pooling the data from both samples, constructing a weighted average of p hat 1 and p hat 2. Look, if that sounds complicated, it's just like, we have a sample, right? So we are going to sort of increase our odds of reflecting the actual true population proportion by averaging all the samples we have. Okay, so we're going to take, the cases from the first population and the cases from the second and divide them by the total number of observations. Okay, so it's like you're doing an average between the 2 populations. So x1 is, the number of successes, in sample 1. And x2 is the number of successes in, can you guess it? In sample 2. You get all the points if you guessed it. So, this way, the larger sample receives more weight. All right, perfect. in conclusion, this is our standard error. So remember, standard error is the standard deviation. So we're factoring in this calculation here that we just talked about here, and then 1 minus p hat, and then 1 over n1 plus 1 over n2. It's great. So what do you guys care about? Well, what's the formula? Well, here's HO. Again, very similar to before, that the proportion 1 is equal to proportion 2. Or we can write it this way. I really don't care how you write it. Again, ding! I prefer that one. Prefer the first one. And here's the test statistic. And there's p hat. And basically, all the other steps remain the same. So, perfect. Let's go. Oh, boy. You might want to pause it. Take a moment. You know. Read it. So, what do we got? We got a product was tested in 2 different cities. Great. Vancouver and Toronto. Love it. Equal amounts of money was spent on advertising. Okay. However, in Vancouver, we strictly did television and newspapers. But in Toronto, we did YouTube because they are so cool. So after 2 months, surveys were conducted to estimate the consumer awareness of the product. In Vancouver, aha! So we might go ahead and say that this is, you know, p hat 1, 631 out of 1,000, right? And we can say that n1 is 1,000 and that x1 is 631. There you go. So they were aware of the product, but in Toronto, the cool cats in Toronto with their cool city, it was 798 over 1,000, right? So then we got an n2 of 1,000 and an x2 of 798. Okay, test the hypothesis that the advertising campaigns had different effectiveness levels with an alpha 5%. Huh. So that's not giving a direction, right? It's not saying more or less than, it's different. And when you have that, it's going to be a two-tail test. Two-tail test. So there you have it. Next slide. Let's take a peek. So what is our HO? Well, you can always reliably say that P1 equals P2. Notice how we don't have the hats in here, because remember, we're talking about the population proportions. And what is our HA? Well, again, it really matters which one is which, right? So what are you calling P1? What are you calling P2? It'll be clear from the numbers which one is which. So you don't necessarily need to say, like I'll see when you write out your calculations, but we're going to say that P1 does not equal P2. I suppose if it's a two-tail test, it doesn't really matter which one you put on which side, but it'd be a little weird if you did P2 first. Level of significance is 5%. It's a two-tail test, right? It's 2 tails. So we're going to have to split that in 2. So we're going to go alpha divided by 2, which gives us a z of 0.025, which is equal to, it's going to be plus or minus, because it's going to be on both sides of the curve. Go to your t-table and look up 0.025 right here, degrees of freedom infinity, 1.96. So 1.96 plus or minus, right? Because it's going to be on both sides of the distribution. So I usually recommend you draw this. So negative 1.96, positive 1.96, reject HO, reject HO. So you might say, you know, if Z is greater than 1.96 or Z is less than negative 1.96, reject HO. Don't skip the step, it's important. So from the data, we already wrote out all that other stuff about P hat 1, right? That was 631 out of 1,000, so P hat 1 was 0.631. You don't need a calculator, right? Just move the decimal in 3 times. Just trying to give you a quick trick. And then this one was 798 over 1,000. So 0.798. Hopefully you use the trick. And then we can find our pooled p hat, right? That's the one where we go x1 plus x2 divided by n1 plus n2. So 1,000 plus 1,000, so 2,000. And not going to give you the intermediate numbers. You'll get 0.7145. Now everything else, I think we can just plug into the formula. Okay, remember DO still there, still 0. So let's see. P hat 1 was 0.631. P hat 2 was 0.798. Divided by, now kind of draw yourself a nice big line here. So P hat was 0.7145. Then 1 over 1,000 plus 1 over 1,000. Right, if you're wondering, this is a 1. Sometimes people ask me, is that an L? No, it's a 1. So when you do all the work, you might want to pause the video. I'll give you some intermediate numbers. So there's the numerator, negative 1.67, and the denominator, 0.0202. For a grand total of negative 8.2673. Wonderful. Well, this is also, again, I usually make the numbers a bit closer, right? So just have to think a bit more. But this is a very strong reject, right? Like we're clearly quite a bit smaller than negative 1.96. So I believe on the next slide, we're going to take a peek at that. So yeah, I already said that. So, all right, this is just a fancy way of writing it. This means absolute value of Z. So absolute value of Z just means you get rid of any negatives. So, so it was negative. I'm just going to rewrite this because I don't want to be confusing here. So I'm just going to say because Z is equal to negative 8.2673, and that is less than negative 1.96, we can reject HO. Remember, HO was that P1 minus P2 was 0, or P1 equal P2, right? So in favor of HA, what's our conclusion? So, at the 5% level, oh my goodness, I hate writing this word, the proportions of consumers who were aware of the product in Vancouver and Toronto, what? They differ. Remember, that's what they're asking. Are they different? And we can say, yeah, at the 5% level, they were different. How different? Who knows? But we can say that there was a significant enough of a difference that they were indeed different based on the data. All right. So, these are long questions, you guys. It is what it is. There's a reason they're 8 marks long. So, last one here is, what if we have small sizes, sample sizes for testing the mean difference? So, now all of a sudden we're back in this box here. So, we're looking at sort of part B here. Let's take a look. So, if either or both of the sample sizes are small, so less than 30, okay, so either or both. We have 2 problems. Central limit theorem doesn't guarantee any more the normality of the sampling distribution. The estimates of the standard deviations are unreliable, and the z-test is not appropriate. So we're going to have to use a t-test. Okay, which actually has a special extra calculation. Accountants get very excited about extra special calculations, in my experience, in talking to my accountant. Side note. So yeah, we have an extra special calculation for what's called the pooled standard deviation, and then I kind of say, see the formula sheet. And what we're talking about here is, if you look here, in the formula that has the t, so for the test statistic, there's this SP and that stands for pooled standard deviation, and it's this big whopper down here. So you got to calculate all this, and it's so big that it's like, let's put it as a special calculation on the side. Okay, so keep that in mind, and you'll see it in the example. And also, check it out. Remember, DF is degrees of freedom. So degrees of freedom is there's two populations, is add up the total number of samples, so N1 plus N2, and then subtract 2 instead of 1. So yeah, that also happens. What are some assumptions? You know, this is the background theory stuff, but assumptions we're making are both populations are approximately normal. Both populations have equal but unknown variances. And the size of either or both samples will be small, and the samples are selected independently. So here we go. Basically, I don't even do a question, I don't think. I just leave it for... There's nothing different here, right? Like, I've just pointed out all the differences. The big thing is that you need to calculate this. And there's nothing special about calculating this. You have to plug in all the numbers and do the algebra correctly, right? And then you have degrees of freedom. Is N1 plus N2 minus 2. That's another big thing. You know, here's the test statistic with their special calculation. So it's not a cop-out, because there's really nothing special about these questions. There are some in the homework, and you know what? When I make when I do my extra question video, I will try to see if I can find one for a t-distribution that I can throw in there for you guys. So that's the end of our notes, and I really do wish you guys happy studying, because I believe our midterm is coming up. And happy studying. I provide all the materials on the Moodle. And you know what? I really enjoyed this, and I will see you guys next time. Bye-bye.